Hello everybody, got a Genius G1100 1 amp, 1.1 amp battery charger, 1.1 amp or 6.3 volts, 1.1 amp. So it's the baby of the range. I don't know if it's a current one, I think it's a bit old, but this is another warranty. Chop the wires off and we'll send you a new one. It's been sitting around for a while apparently. The person who sent it to me told me. So I just had a few moments to spare. I thought we'd have a quick look inside and see what is happening. So the first thing, I think it's reported dead, so let's stick some of Her Majesty's volts up the hole. This is an isolated supply. I'll do an explanation of the rig I've got for isolated mains, because I think most of you would find it useful, or even perhaps life-saving. You never know. So anyway, don't do this at home, but I'm an expert and I've got curly hair, never used to have until I had a few shocks. Stuff the wires in the heel. I'll demonstrate this rig to you and show you why it's a safe bet. Okay, so we're in there. We've got a voltage supply of 100 to 240 volts AC down there. That's the battery charger. If you've got one the same, then carry on watching. If yours is blown up, this might be a very useful video for you, mightn't it? It might not be, but it might be. Right, okay, so power on. There's no chance of that shorting out at all, is there? So let's just turn the power on, stop talking and start debugging. Power is on, 240 volts, all the lights are on, and nobody's home. No lights, no flashy, nothing going on. Absolutely dead. It's got these holes in it, look. You can screw it to the wall if you want to. You can see that through hole there and a through hole there, so you can stick her on the wall. I prefer to do that, and then nobody can borrow my battery charger unless because they're all too lazy to take the screws out. There we are. Anyway, that's it. So let's take the back off her. Let's turn that off. What screws have we got down here? Oh, I think we just take her apart. Have a look inside. We've got the old triangular screws. They are the most dumbest of dumb screws, dumb screws, because they've got 3 sides, right? Now, if you double the number of sides on there, you get, what do you get? You get 6 sides. And what's got 6 sides? An Allen driver. And if you're a bit screwed because you haven't got these, they're getting more common. You get them in kits and things. They're more of the triangular security screws. You can actually just use, this one's an M2.5 hex driver, and they work. Hex drivers work pretty well. And to prove it, I'm going to show you. Oh, so the focus has all gone funny. Yeah, so an ordinary hex driver gets those. I suppose what you would call an Allen key, gets them out a treat. How about that? If you learn nothing from this video, that could save your day as well, couldn't it, in a certain situation? And see how they fit. Did you get vertigo? I did. There, you see? Can you see how they fit in there? Cool, eh? Can you focus any closer than that? No, you can't. That's all she wrote. But yeah, all the same, not bad at all. So pull the screws out, carry on screwing as it were. Pull the back off. It's kind of a rubberized coated plastic. It feels rubber, but it's hard and brittle, so it's some kind of rubberized paint. You know, stuff they put on boots and things. You've got a nice seal on it. Look, a nice gasket seal around there. Not bad. Nice piece of polycarbonate as well. It's true PC. Can you see that? The recycling mark polycarbonate, which is strong. Same stuff as they make aircraft windows out of. Right, so here we have the board. Right, so we've got nothing coming out of it. So the name of the game is to get this thing out of here. Yakking on about that and nothing, aren't I? We want to find out how to fix it. That's what we want to do. So pull that out. Pull that out. Give it a bit of a pull. Should have discharged by now, shouldn't it? Oh, no, yeah, it has. Just joking. Alright, hold on. Give that a bit of a twist and just kind of wrestle the little thing out. Okay. Right, so down this end of the board we've got the main power wires and the filtering for the power for the going out to the battery charger leads. So in order to release this so I can work on it, I think I'm just going to unsolder the low voltage side leads, because we don't need those, because we know at this point there's a catastrophic something going on somewhere between here and here. Right. Pull it free of that silicone. Come on, baby, out you come. There we go. That's one. And then the second one is this one. So that's negative, this one. Okay. You see a little tap on the bench. It's a good way to soldering those. Makes your bench all covered in solder. Make sure it doesn't drop into your laps. Right, so we can fold that out on there, and you can have a better look at what's going on top as well. Okay, so let's have a look inside this NOCO Genius G1100. There she is. Now, we've got all the common components of a power supply. I think we've been through them on other videos. If you're just here to look at the Genius G1100 fix, then you might want to scoot through to the end if you just want to know how to fix it. But of course, I'm showing you how to diagnose it, which is a different thing altogether. So after a diagnosis, you should be able to fix more than one of them, i.e. not this specific fault, but a general better understanding of how this circuit works, which is the whole point of the channel. If you want a quick fix, then go and look somewhere else. But you can see all the stuff on here. I'll just give you a brief overview. You've got the mains coming in, you've got a power supply wire-ended fuse, you've got a varistor, voltage dependent resistor, which when the voltage from the mains goes higher than about 275 volts, that thing will start to conduct and try and absorb the transient to protect the rest of the circuitry from an over voltage on the mains, either lightning strike or a power cut when the power comes back on, or some other kind of disturbance on the mains power supply system. Could be an end of an extension lead and you've got something else plugged in there, like an electric drill or a sander. Will generally, on a coiled extension lead, electric drill and a sander being operated at the same time as these kinds of battery chargers, will destroy this switching, the high voltage FET switching device. You have to watch out for that. Then you've got a filter capacitor across the mains, which is working in conjunction with this common mode rejection choke, which prevents noise from the mains going into the power supply, and also switching noise from the primary of the power supply being transmitted out onto the mains wiring and transmitted and interfering with other things on the mains as part of a CE requirement. Okay, this unit, as I said, has had the leads cut off it. So you've got your primary high voltage B plus side smoothing capacitor, 32 microfarad, 400 volt, Samsung SAMXON, very good make indeed, very good make. You see them trashed on the internet, but generally they are pretty good. I don't see a Samsung, not Samsung, Samsung XON capacitors. I don't see one and think, oh dear, there's a capacitor, it's probably that's gone. They're usually pretty good. And here we've got, so that's the power producing roughly twice the mains via a bridge rectifier, which is where is the bridge rectifier? There is the bridge rectifier, BD1 there. Okay, so that's taking the unrectified mains, shoving out as rectified DC, which is smoothed by this capacitor here, the big reservoir capacitor, and there's a HF bypass capacitor and a series of 200k resistors, or 200, and that probably provides the DC startup low voltage, a leakage path to 0 volts to charge this capacitor somewhere. The bootstrap capacitor is charged via that DC dropping system there, high impedance, and when that capacitor is charged up, then the power supply chip, management chip, which is this one, will step in, start up, and then start the power supply up. And when the power supply is running, we've got a diode power supply from here somewhere, probably that one's not populated. One of these diodes here will provide power from a winding on there, so that when the power supply is up and running, it's got a stable DC low voltage power supply to power the electronics inside this chip, which then will provide the drive and the monitoring and the control for the FET there, field effect, or high voltage switching transistor, something like a 600 volt FET there. We've got, is that 1 ohm resistor or a 10 ohm resistor? One with 0 is 10 ohms. I'm surprised by that. There should be a current detection resistor here, which is wired in series with the primary of the switching transformer, which monitors the switching current flowing in the FET. It's down here somewhere. We'll look at this more closely on the circuit diagram. So what are you going to do when you've got a board like this, which is, as explains, completely dead? What are you going to do with it? You've got to decide whether it's on the primary side. This is the primary high voltage side, which is referenced to the mains. So if you plug these wires in, the mains in, you've got live mains on this half of the board, that half there. So beware, there's some high voltages and it will spoil your day. And then don't switch it on outside the box if you don't know what you're doing. I'm assuming you've got experience working with high voltage, or certainly common sense. One thing to do is always keep one hand in your pocket or one hand away. If you've got one hand on a metal structure like my shelving, and you touch the live mains, then you're going to get a nasty shock across your chest, and it's a shocks across your chest which kill a healthy person. The shock of having a shock can kill an unhealthy person, but that's a different story. And I'm running, just to recap, I'm running on an isolated supply, so neither of my mains wires coming here, I can touch these but not together. Neither one of these is referenced to the mains by a copper connection. The only connection is the flux in the isolating transformer over there on the bench, which prevents me touching one of these wires and touching a grounded item like a soldering iron and getting a shock. Might get a tingle, but I'll get anything serious. And there's other ramifications of that as well. I don't want to diverge too far because I just want to get this in one take. Right, so what we've got here is a power supply management chip, and it's always useful to have a quick shufty to see if you can identify it. And it says IFF equals 220 on that SOT23-6 chip down there. I don't know if you can read it with the camera. I hold it still, turn it round. I read it upside down because I have special upside down reading skills. Not, can you see it there? IFF equals 220. There it is. There she blows. Say hello to an IFF equals 220, right? Now, who makes that thing? I've looked on ChatGPT, I've looked on the usual AI thing on Google, and it comes up with a load of old crap. But what I did was, sometimes when you get these things and you can't identify a chip, obviously it's going to be useful to us to be able to identify that chip. A, if we want to buy one, and B, if we want to see what the schematic is, because it's probably been more or less copied. The schematic on here, the circuit, has been copied off the data sheet. We'll look at the data sheet in a minute. And if you, it's quite useful actually, because if you look around on these boards, usually if they can, they will do a deal. The manufacturer will do a deal with the manufacturer, the component supplier, and say, oh, we want this particular type of chip. And the first thing that, trust me, what I'll ask you, I've been through this many times, is what other chips on the board that we can supply you. If you agree to use our chips instead of someone else's, then we can organise a discount, a way of upselling from just buying one power supply management chip. So the manufacturers for mass-produced, the manufacturers of the devices will be competing for business with people like NOCO. So I looked on here, and this is this is the low voltage side. There's a insulation chasm across there, so that you can touch this part here and not get a shock. This is the part that goes off to your charging leads and your battery clips. This is the side which is high voltage, and the only link in between these two are these two class Y fail-safe capacitors, and they connect the low impedance side of the main supply to the 0 volt rail, usually on the secondary side, and their job is to conduct RF noise to ground through the mains wiring. Of course, it's got no earth. It'd be better on an earth connection, but the neutral is in theory at earth potential, and it will provide a lot of path to ground for any RF interference that's being generated by this, rather than transmitting it out of the leads that go to the battery. You can see there's an inductor there, a filter there, which is on the output leads. Again, a differential filter, common mode rejection filter, so that any common mode noise, i.e. both conductors going up together, will be cancelled out and filtered and not transmitted down the leads to be radiated into space, interfering with people's pacemakers and stuff like that. You've got your old switch there. So anyway, on a high voltage side, low voltage side, who's the chip manufacturer? I couldn't find it anywhere, so I went to the next best thing, which was to look what else was on this board. And you can see that the logic and the analog board is down here. You can often see a little fissure, or maybe a little shit stain on the board where the magic smoke has blown out. But as you can see, everything on this, including the solder joints, which you should look at in great care. Remember, I'm teaching you how to fix power supplies, not this specific one. But if you've got one of these, this is going to make an awful lot more sense to you, isn't it? Yes, it is. So here we are. There's the chip. It looks okay. There's no exploding marks, no bits of plastic missing, no fissures in the top. It's all clear. There's no little pimples. Sometimes you just get a little tiny blowhole in there, and where it's farted its contents out. But generally speaking, rectifier looks good. All the caps look good on the top. They look pretty sexy, don't they? And they're all, none of them are bulged. There's no leaking or anything like that. What about this one down here? That one looks good as well. So this resistor's got no cracks or splits in the resistor. Large resistors like this undergo a sudden shock. Often you see cracks in the paint on the top. There might not be any burning, but if you see cracking on there, beware, because some of them are wire wound. This one isn't. I think it's a metal film, but yeah, look out for cracking on the resistors. There's the fuse. We can't see what condition the fuse is, so I'll have to meter that in a moment. But generally speaking, you can see everything looks pretty good. And if we go underneath and just look at the solder joints, I can't see any of those pins not being soldered. If you can see that one there, there's a very good indicator there actually. I can get any closer to that view. I don't know if I can. No, I can't. I'm going to try this. But this is a particularly pernicious type of failure. And if I can get any closer, can I get closer? And maybe this one hasn't, yeah, there it is. Can you see, can I get even closer than that? Yeah, I can. Can you see on this one, there's kind of a ring around the base there, all the way around the unit. It's a bit clearer in the light. If I tilt it that way, you might be able to see it better. But when you're looking at a pin header or a relay pin, look around there, because if that vibration, the solder joint is the thinnest there, and if it's cracked, you can even get a kind of a spark action going on, and there's the faintest witness line around there. But on relays, on things like NEF washing machines and Electrolux and things like that, on the controller, that crack around those pins is enough to stop it working. This is not a particularly bad example, but I can see the starting of that thing where the thing's been flexing, and if you're in a washing machine especially, you get this flexing thing going on. But people have inspected boards and not spotted things like that crack. So my point is really, okay, there's electronic components that go, but always have a really good deco at the board, a really good look to see whether you can see anything wrong. For example, there's a, you see that? I would say it might not be giving us problems at the moment. Can you see that joint there? That is a dry joint on that capacitor on the other side of the board, one of the smoothing capacitors. You see that? So that's potentially a failure. So that's got to be touched up anyway before we put this back together. Then looking on the high side of the board, have we got any other particular nasties that we can see? Leave a comment if you spot one that I haven't seen. I'll give you a prize. I'm not telling you what it is, but there'll be a small prize. Right, a competition. Alright, so can't see anything else wrong with it apart from that pin and that capacitor solder joint. Always have a good look, moral of the story. And there she is. I did kind of explain that we've got two power supplies here. One is the charging power supply for the actual battery power, if you like, to charge the battery, and the other one's a lower voltage logic supply to provide regardless of what the demands on the battery are in terms of charging, you still need some demand and some power here to run these chips. Okay, now you can see the Zener diodes and rectifier diodes here, a bunch. There's a network of diodes there and a transistor, I think. I'm not sure whether this LM324 requires a negative rail. It probably doesn't, but if you're working about zero on a current gain or very close to supply rail, sometimes you need a positive and a negative supply rail so that you've got some headroom for the electronics to work into. Obviously, if it's a current sensing resistor for the secondary side which goes to ground, just to 0 volts, you've only got a few millivolts, and this has got inputs have got to differentiate and work within a few millivolts of the supply rail, and it's not an ideal place to be working in, especially in a noisy environment. So sometimes there's a negative supply rail required as well. Anyway, I'm not going to go into that any further, just bear that in mind. Right, and the other thing is your switch here, so that's the switch for you. These switches, as I explained, are very prone to getting clobbered. If you just bang the front of the power supply, whether chuck it in the toolbox or drop it and it hits the switch, there's a dome in there and it collapses the contact, and often it doesn't feel quite right, but it's still clicking. But continuity between these are common pins on both sides, so that one and that one are connected, and that one and that one are connected together, and when you press the button on this push to make momentary switch, it connects that side to this side, that side to that side. Right, so you've got to check your switches working, but this is totally dead, nothing happening at all. So what we're going to check anyway, so let's get on with the checking. I'm going to unplug my makeshift test power and we'll get down and dirty with this, see if I can get this to lie flat. Okay, so let's have a quick look at this. We have on here the Holtec microcontroller, which is on here, which is controlling the smart function of the smart battery charger. Cheap Holtec Taiwanese company, used to be 4-bit 8-bit microcontrollers, one-time programmable. Probably moved on since then, they may have become more sophisticated. So I thought I'd have a look at the Holtec datasheet for the FF220, the FF equals 220, which is this small tiny power supply management chip down here, which we looked at I think already. I can't quite remember, it's a different day, I can't remember, so I'm repeating myself. It's tough for the moment. Very wise if I turn it around for you, isn't it? Yes, it is. Where are we? Oh, no, lost the thing completely. There it is. You might just be able to see that IFF equals 220. Anyway, it's a Holtec chip. I looked it up and found the datasheet. Would you believe it? So we're just going to have a quick chat about the datasheet at the moment. So where's the datasheet? PDF viewer. There we are. So here we have our datasheet. IFF 2200 or 220. And if we go up to the top, It's a smart jitter PWM flyback controller. Smart jitter means they jitter the frequency of the clock so that any EMC or electromagnetic emissions which are above the limits, instead of having a narrow peak of narrow bandwidth, you've actually got it spread out over maybe a 16 or 20 kilohertz or 30 kilohertz band spread. A bit like spread spectrum really, but it's hopping the primary frequency of the switching mode power supply all over the place, so you don't concentrate the energy in the magnetic EM radiation into a narrow high level peak. It spreads it out like smearing it out with a knife on butter. Smear it across the bandwidth, then you might not go over the limit line when you're doing your accreditation approvals for EM standards, EN or American FCC and so on and so on. Right, so it tells you all about it here. And we've got there's a typical application circuit. There's a more detailed one later on. We've got the IFF 77366. The IFF equals DNN. So ours was made in D is a date code, so it's the year code, it'll be there somewhere. And the product code is FF, and NN is the week number. So it's year code and week number. Okay. And so we've got the RT37736GCE, which is, what's the difference? And the other one's got an overcurrent pin. There it is there. What have we got? So we've got this one on the left, and you can see the BNO and the PRO pins are different. These two pins, one here and one here. BRO is brownout detection, which when the power dips, it will presumably reset the power supply. So to reset your electronics, you're going to shut down and start up again, I presume. And PRO is a protection input for over voltage protection. When the voltage goes too high on the input, it shuts the power supply down to protect the FET from destroying itself. And if we just whiz down to the actual application, it gives you a full explanation of this chip in here. So I'll put this link in the description of the video so you can have a look at it and knock yourself out. And we're moving along. What have we got? We've got all the currents and all the parameters. PWM frequency is 65 kilohertz. Jittering range of plus or minus 6%. And the jittering period is 16 milliseconds. So every 16 seconds it jitters around 6% or so all over the place to spread out the actual peak of the energy in the EM emissions from the product, from the switching primary switching frequency, I suppose, and the harmonics as well. All that down there. So if we just go on down, this is our application circuit there. Can I make that bigger? No, it's as big as I can make it. I'll spread it up. Okay, so what have we got here? We've got AC mains going in through a fuse up on the top left hand side. AC mains in there. We've got that would be normally a thermistor. There's normally a negative temperature coefficient thermistor in there to reduce the inrush current. When the power is on, thermistor is cold, there's a 20 or 25 ohm resistor in there. As that warms up, after you switch on, it starts to warm up, and as it warms up, the resistance reduces down to a couple of ohms really. So it's an NTC. There isn't an NTC on this unit. There is this capacitor here, which is right. So what we got here is input fuse there, and then the capacitor there, and then the bridge rectifier. Or input fuse is this one. Where's my pointy thing? There we are. Input fuse is this thing here, standing up. That's a varistor, which is not on the circuit diagram. That's a device which, when the voltage across its terminals increases above the set limit by this, defined by the specification of the part, that it starts to conduct electricity. And this will be a 275 volt AC varistor. So if the input voltage across the mains goes over 275 volts AC, this starts to conduct and the current will flow through here to limit this surge on the mains, whether it be from lightning strike or a power cut and the power's coming back on, or some other kind of disturbance in the mains. If you plug one of these battery chargers in at the end of a long extension lead, they've got amps onto a generator, and if the generator regulator or the governor goes wild, you get mad voltages, and these things just burn out. They can't take much. Therefore, very, very short term, sub 250 milliseconds surges to conduct them away between live and neutral, basically effectively clamping the voltage across the input to the unit. There's a common mode choke. That's to both live and neutral go through these two windings, live and neutral, and that is to stop any switching. Common mode means it's on both lines, and it'll let the common mode go through, but anything that's not on one on the other, it will couple and cancel out. So it will cancel out the noise on both lines if they're out the out of phase noise, which is switching noise, which prevents the switching frequencies going down and radiating out using the mains lead as an antenna, stop it interfering with other equipment. There's a main smoothing capacitor, which is this one here. We talked about this earlier. Big electrolytic, looks in good nick. Then if you go back to the diagram again, you've got your bridge rectifier, which is this thing here with 4 connections on. You spotted that. Yep, there's a bridge rectifier just there, that little square block BD1. And then it shows you a filter capacitor here, and this is your AC 0 volts just there, filter capacitor. And then you've got your rectified DC mains smoothed by the capacitor up here. That's roughly twice the input voltage of the main supply. It's not twice the voltage, is it? So it'd be √2 times RMS. So if you had 100 volts going in here, you would have 140 volts DC or thereabouts on the B plus line. We're working at roughly 220, I think, on my rig. So this should be 240, 250 volts probably DC on here. Okay, so the DC comes out, and you can see that there is a midpoint potential divider on the AC there, which is acting to charge the... Do you know what? I think they've wired that on the wrong place. That would normally come from there. Interesting. The midpoint of this is basically a virtual 0 volts, isn't it? So you've got a I understand all the diodes in that position, or do I? Anyway, this provides the power for your VDD, which is low voltage power, to run the power supply management chip here. Okay, so that's a DC voltage. You turn the power on, the power comes down here, gives this some DC voltage to start the unit up, waits for this capacitor to charge. When the charge reaches a certain voltage, it switches on, starts the power supply up, and when the power supply starts, you get power generated in this winding, which goes through that resistor, which I think is that 10 ohm resistor we saw, a rectification diode, and provides the low voltage DC for the chip whilst it's in steady state operation. Now there's a protection, there's a thermal protection, thermistor for protection and overheating. When we're not using that, we're just using the comp pin, which is the enable pin, effectively enabled by this photo transistor, which is part of this optocoupler device just there, U2. Okay, so U2 is the optocoupler, and half of U2 is on the high voltage side, which is the receiving transistor down here on the left hand side going to pin 2, and the other half is on the low voltage side, which is monitoring the output DC voltage. And you would set, these are normally a set 1.5 or 2.5 volt standard voltage source, but they're normally precision voltage sources because Zener diodes don't have a sharp enough switching knee. They're basically too inaccurate. So this would be one of the RT voltage source components for, and as the voltage on this pin goes up and down, this turns on and on and turns your LED on and off. Okay, so you set the voltage of your output of your DC side by the ratio of these two resistors, programming the input switching voltage there to turn the voltage reference on and off, turn your LED on, shine the light on this part onto your photo transistor, so when the voltage on here comes up to the DC voltage set point, this turns on, shines on there across the, there's no electrical connection, it's just the photons traveling across the device onto the photo transistor, turns the photo transistor on and shuts down this power generation circuit, switches off the switching to the FET. So that by pulsing this up and down, you can regulate your DC voltage. That's how the regulation works. Now on this side we've got the B plus, or the 220 volts or so DC, goes through the primary of the transformer and down through the FET. This is that big FET just here, the power FET, I suppose you'd call it, this thing here. It's got 3 legs on it, and then goes through to this resistor down here, which is the current sensing resistor, and also a capacitor here for current sense CS on pin 4. Okay, so if the current through the primary goes too high, then it returns to 0 volts. Okay, I've freed it from the enclosure. The mains is connected at the moment, it's not turned on. I freed it from the enclosure because it was just like getting unruly and ridiculous. I've got my 01 connected by my driver to the top of the screen, so there's just a serial port in the back of the unit and a monitoring service on Windows. If you want the driver, let me know. It's quite handy. So there it is up the top. That's the reading on my 01 desktop multimeter, and it emanates or originates to the world through these 2 probing devices. Not the best quality probes. Right, so anyway, look, if we go back to the schematic, we're now going to go through a debug with the schematic with a live. So AC mains in, let's check the fuse. There's no thermistor. Let's check, go straight through and check the voltage on the reservoir capacitor. That's this big one on the back. This is the capacitor there, and we're going to check on the back of there when we put the power on to see if rectified mains is reaching that capacitor, thereby making sure that it tells us that the fuse is okay, the rectifier is okay, and we've got roughly √2 times the main voltage on there through our bridge rectifier. So if I just turn it on, right, we're alive. We are alive, and I measure the voltage across the transformer. Oh yeah, what are you talking about? Capacitor, there it is. So I can touch this end because that's the safe end of the board. That end is definitely not safe. So there. We've got 270.38 volts, so we've got DC voltage. The fuse is good, the rectifier is good, there is power. Now the next place we're going to measure is across the bootstrap power supply capacitor, this one. If this is trying to run, it's going to need some DC voltage on there, and the so let's check that small capacitor. That's the one, this one around the back, right around the back, that one there, C whatever it is, that's the bootstrap power supply capacitor, and that originates, just be careful with this because it is turned on. It is in fact those 2 connections just there. Oh, there we got 12.137 volts, which is good. That means that there is power. It means that this chip is not shorted. Okay, so it doesn't mean to say that this power supply chip hasn't failed, that there's no attempted switching going on, but there probably is. So let's just check on the secondary side. So we might as well take a look at the main power supply. Remember, there's 2 power supplies on the back of this thing. There's the one for the battery charging voltage or power, and one for the this row here for the logic. Okay, so we're going to check on the back of these 2 to see what we've got in terms of power. Right. So checking on the back of the smoothing capacitors for power. On the DC charging sides, we've got nothing. We've got 229 millivolts. It's actually not doing anything at all. So there's no power on the secondary side. Okay, now we could try debugging further. If you had an oscilloscope, you could check by putting a probe near the transformer and seeing to see if the thing is trying to start up. We don't have the means here. I have the means, but it's no good you trying to me showing you how to debug with a scope when you don't own a scope, is it? So what I'm going to do is I'm going to turn the power off. You're going to leave it for a few minutes for any dangerous voltages on this capacitor here to dissipate. I don't know what's on there at the moment. We'll just check it to see what it's reading now, if you like, as an interesting Yeah, we've got 206 volts on there at the moment, which you don't really want to get that out of your shirt, so I'm just going to short that out. Okay, so that's killed that power supply. Always makes me jump, even after all these years. Right, so we've got a short. We know we haven't got a short on the primary side, so we know that there's no power emanating on the secondary side. So if we stick our meter onto continuity, there, just put it on resistance. Okay, and then I'm going to meter on the back of the smoothing capacitor on the battery charging power supply, and we've got 0.398 ohms, 0.399 ohms. That is not normal. Okay, so we have a short on the secondary side of the board. Presumably, if I measure these components up here, which is the other power supply for the logic, we might see something quite different. Let's try that. See if we can see the output from the meter, the excitation voltage charging the capacitors. Right, let's check on the back of these reservoir capacitors there to see what reading we see. So they're discharged at the moment. Let's just make sure they're fully discharged. And then see what happens. So you can see the capacitors are charging and it's open circuit, so there is no short on the secondary side. If I go back and check the actual DC voltage there, we'll have charged it to, there you go, 0.2437 volts. So I don't think there's a short on the other side, but we've definitely got a short on this side. Now if we go back to looking at the circuit diagram. Okay, let's have a look at the circuit here about where the rectifier is for the low voltage. We have a short across these 2 points, VO plus and VO minus. And somewhere around here, there isn't much on the board, but there is a short, and we think we know that it could be around here. This diode could be A, because it's a common mode of failure. And if you look at the circuitry there, if you have a short between the in this area, between this point there and the bottom of the transformer, the 0 volt rail, then it's probably the diode that's got short circuited. So we might as well, without further ado, is go back to the board and check the diode, because it is a common failure mode. Okay, across there is a dead short. Okay, so I'm just going to snip the diode, snip the top of the diode here. Okay, snip the wire on the diode just there. Okay, so now we've got a snipped connection, no physical connection there. And let's just measure that diode again across this big positions here. And now there isn't a short anymore. You can see the capacitors charging up now. So just to confirm that, if I meter directly across with the one cable on the diode there and the other one to there, there you can see it. So the diode is short. Let's get it out of there, shall we? See what it is. Come on, you bugger. There it is. Oh, that's hot. Right, we've got an B3100L, which I mentioned before, is a Schottky diode. It's 80 volts on 100 volts, 3 amp. Okay. Now, did I mention about Schottky diodes before? If I did, fast forward. But Schottky diodes do not like to be over voltaged. If the voltage across the Schottky diode breaks it down, they don't have a junction, it'll just fry the diode very quickly. Silicon barrier diode won't suffer a problem like that. It'll just break down, avalanche, and then when the voltage across the diode reduces below the avalanche voltage, it'll just recover and away you go. So yeah, more efficient but a lot less reliable. The Chinese branded ones, this is a PEC 7459. I don't know if PEC is a manufacturer, but the cheap Chinese ones don't really work very well. They're absolute pants. So I'm gonna just stick a diodes, incorporated diode in. Let me have a quick look and I'll see if I can find a something from a power supply. Yeah, look, I've managed to salvage this part from a power supply, RB085T. That's an 80 volt 5 amp twin Schottky in there for a bridge power supply. So there's a diode, anode and anode going there to the cathode there, so there's dual cathode, so I could link those two together and stick that in. Let's just stick that on the back of the board, shall we, for the time being. Okay, so let's just solder this thing back on here. I'm going to put it across the same pads as the remove the faulty diode from. All right. Right, she's in position. Double check the polarity is correct. Third leg's not doing anything, it's just dangling around in the breeze, as you can see there. Look, I just tacked it across because it was a handy Schottky diode. Turn it on. Hey, we've got power. Did you see that? You probably didn't see it, did you? Not going to get much action out of this thing until it's got a battery connected at the other end. As soon as the battery goes on. Right, ready? Yeah, she's working. So it was that diode that was faulty, alright? Not fantastically satisfactory in terms of a diagnosis. Quite an easy one, but as you know, it's always going to be the easy faults are the ones which happen the most, and therefore they are most useful to broadcast how to change it. So we need to get a decent quality SB3100 replacement diode to go in there from Diodes Incorporated or On Semi, I would suggest, or Rome. A good quality one will probably not die. Anyway, so a decent diode in there. I'm not going to bore you with the reassembly. These packages down here are two FET packages, FET switching packages on the DC outlet lines for the battery, and I know on C-Tex there's a similar package, but yeah, they just blow up a lot on the C-Tex ones, but I haven't seen any NOCO ones with it blown. Check your switch, make sure it does the beepy thing. So I'm pressing the button, I'm metering just there. There you go. Make sure your switch is alright, because you get a bump, it blows them up. I think it's okay. I'm not going to bore you with the reassembly because I'm assuming if you got this far you're perfectly capable to put it back together. So thanks for watching. If you've got any particular problems, let me know. Got any comments, leave a comment. And smash the subscribe button if you're not already subscribed to help me out with this, even if you only need this for your own battery charger. And then leave me a like down on the like as well, I'd appreciate that. Yeah, thanks for watching and good luck if you're repairing your own unit.